Tashin Deleg everybody. So last time we have done with ray optics. So without doing much recapitulation, so today I would like to do a few problems of ray optics. So this is my first problem. So whenever we do problem, we always first we read problem properly and try to understand the problem and try to get the concept and try to understand what are the given and what is to find. So this is very, very important, right? So the first problem I have is the radius of the curvature of two spherical surfaces which is lengths of recurve focal lengths are not same. It form an image of an object. The surface of the lens facing the object and the image are interchanged. Will the position of the image changes? This is the question. Alright. So to answer this, first you have to know what is the problem, right? So the problem is that I have a convex lens, a spherical lens. This could be a convex lens, and these two curvatures of a different radii. All right. So therefore, if I interchange this, all right. So will the focus or focal length remain same or not? All right. So to do this, what we have to do is this is all about designing a lens. So how to design lens? We have what we call as lens maker formula. What is that lens maker formula? Lens maker formula tells about this. This is lens maker formula. This is lens maker formula. So this is a lens maker formula, and now R1 is the radius of curvature of a first lens surface, and R2 is the radius of curvature of second lens. So now the problem says that if I interchange the radius of two curvature, will the focal length remain same? This is the question, right? So now you can hear, right? So let's say this is for first, this is for first, and now after interchanging, all right, after interchanging, this is after interchanging. Let's say I say this is, suppose this is f prime is after interchanging, focal length is f primes. Now our what we have to find is whether f prime is equal to f. Alright. So this quantity remains same. Alright. Why? Because the material doesn't change. And now look at here. 1 by R1 minus 1 by R2 is same as 1 by R2 minus 1 by R1. Alright. So value of R1, R2 remains same. Only interchanging. If I interchange 1 by R1 with 1 by R2, the value will remain same. So this shows that f is equal to f prime. Alright, f is equal to f prime. So that means f is equal to f prime. So this is equal to that. So the answer says that will the position of image change? No. Answer is no. Which determine the position of image? This is a focal point. So therefore, we have to find out a focal length. If a focal length doesn't change, then the position doesn't change. That means the lengths remain unchanged. So this is the first problem. This is the first problem. The answer is no. Why? Focal length doesn't change. If focal length doesn't change, the position doesn't change. This is the first problem. Now, second problem I have is this. A thin converging lens has a focal length f. When illuminated by a violet light, state with reason how the focal length of a lens will change if a violet is replaced by red. So this is the point again. So violet and red. So we have learned last time that when a violet light passes through a glass or lens, when a red light passes through a glass or lens, the refractive index of a violet light is different from refractive index of red. So this is our no. We know that. Let's say this is the refractive index of violet, which is more than refractive index of red. That you should know. Why? Because the bending is more for violet than red. So therefore, refractive index of violet is more than refractive index of red. Now, what I say, the focal length doesn't change. Focal length remains same. And now we have to say that will the refractive index, stay with reason how the focal length, right? How the focal length of a lens is going to change, right? So now again we need lens maker formula. Why? Because now this time it is nothing to do with the curvature, it is something to do with a refractive index. So therefore, I just say this is refractive index of, this is general formula, alright. This is the concept. This is the concept behind this problem, right? So now I say since the violet, so this is for violet, V, alright, then I have this is for red, this is for red, V, alright, V. Look at here. So NV is more than NR. So that means look at here. Look at here. This is going to be more than this. This is going to be more than this. And this is going to be more than that. Then what is going to do, right? So I just write F, alright, V will be more than 1 by F, less than FR. Alright, did you get my point? If it is not, look at here, I can write something like this. 1 by R, 1 by FV, 1 by FV is, 1 by FV is more than 1 by FV is more than 1 by FR. Why? Because NV is more than NR. So which implies that 1 by FR is more than FV. Alright. So this is the point, right? So we will say that yes, focal length is going to change. The focal length of a red is going to be more than focal length of a violet. When we replace a violet by a red, focal length is going to increase. Why? Because refractive index of violet is more than refractive index of red. Again, I will say refractive index of violet is more than refractive index of red. This is the second problem. Now going with the third problem. Third problem says that thin prism of angle 60 degree, that is angle of prism. So angle of prism is 60 degree, or I'm writing the given part. Say given. And give a deviations, that's the minimum deviations, right? Give a deviations, let's say 30 degrees. What is the refractive index of material, right? What is the refractive index of materials? That's the minimum deviation is 30. And what is the refractive index of? This is to find. So now let us take some condition, right? So we say that at minimum what is the deviations? We say the deviation is equal to I plus E minus R1 plus R2. And we also have derived that A is equal to R1 plus R2. This is what we have done last time. Alright. Now I say that if a deviation is equal to minimum deviation, then I is equal to E, that we have done, and R1 is equal to R2. Therefore, condition is that A is equal to 2R and I is equal to 2I is equal to Gn plus A. So I is equal to Gn plus A divided by 2. Then R is equal to A by 2. These are the conditions. Then again I told you that we have to put a Snell's law to derive the refractive index. So what is the refractive index? Refractive index is equal to sine I divided by sine R. So what is sine I? Sine I is equal to Dn plus A divided by 2. What is sine R? Sine R is equal to A divided by 2. Alright. So what is the given? This is A, this is this. So therefore, sine 60 plus 30 divided by 2. Sine, what is that? 60 divided by 2. This is equal to sine 45 divided by sine 30. What is sine 45? 1 by root 2. And what is sine 30? 1 by 2. So therefore it is going to be 2 by 1. So it is this. This is the refractive index. It may come around 1 point something. So this is the refractive index. So what is the refractive index of metal of the prisms? So this is the refractive index. This is the refractive index. This is the refractive index. Alright. Okay, now we will move to the next problem. What is the focal length of a convex lens of a focal length 30 centimeter is in contact? What is the focal length of a convex lens of a focal length 30 centimeter is in contact with concave lens of focal length 20 centimeter? Is the system is converging or diverging? So look at this. System is converging or diverging. This tells you that whether the total or combined lens is convex or concave. That means is it converging or is it diverging? If focal length is negative, then it tells that it is concave. Why? Because it is going to diverge. If a focal length is positive, then it is convex. It is converging. So that is the point here. So what is that? Convex lens. So convex lens I have given here. Focal length of first focal length is going to be plus 30 centimeter. Why? Because this is convex. Convex always has a positive focal length. And then second part is this is minus 20 centimeter. This is concave. Let's say this is convex. This is concave. Now I have to combine it. So to combine it, so this is how I am going to combine. Combination of lengths. We have used a combination of lengths. So our main focus is to find this. This is combined focal length. So how much is it? 1 by f is equal to 1 by 30. Alright. Minus 1 by 20. Alright. What is LCM? This is going to be 60. So 2 minus 3 divided by 60. Alright. So therefore 1 by f is equal to minus 1 by 60, and which implies that f is equal to minus 60 centimeter. So what is the combined focal length? So combined focal length is equal to minus 60 centimeter. So minus implies that, negative implies that it is concave lens or it is diverging. It is diverging lens. And what is the focal length? Focal length is 60 centimeter. Alright, focal length is 60 centimeter. It is concave lens or it is diverging lens. So this is the maybe a fourth problem. Now next, move to the next problem. A small telescope has objective length of 140 centimeter and eyepiece focal length is 0.5 centimeter. What is the magnifying power of the telescope? What is the magnifying power of telescope for viewing a distant object when telescope is in a normal adjustment, that is when the final image is at infinity? This talks about telescope. So let's say, actually the problem is very simple, but the question looks little lengthy. It says that I have an objective lens. Normally objective lens should have a longer focal length than eyepiece, and this is normally used to see a far distant object. That is the job of telescope. And now here, and you are going to keep image at a far point. So keeping image at a far point, we know f objective length is going to be 140. So this is given, and eyepiece is going to be, all right. So what is magnification? Magnifying power is nothing but magnification. Magnifying power is nothing but magnification. So therefore magnification is going to be f naught divided by f e. This is simple formula. We have derived it. And then I say this is 140 divided by 5, and if I cancel out, 5 2s are 10s and 5 8s are 40. So magnification is 48. It has no unit. Magnification has no unit. So this is the magnification. Magnification of this simple telescope is 28. That means it magnified 28 times. Now next problem I have is this. So I will do as many problems as I can. So this is the problem. Find the radius of curvature of the surface of a plane convex lens. Surface of a plane, this is something like this. Surface of a plane convex lens. Alright, whose focal length is 0.3 meters and the refractive index of a material is this. So therefore I say, what is the focal length? Focal length is 0.3 meter. What is the refractive index? The refractive index is going to be 2:1, means second median with respect to first median, or else I can keep this as n, no problem, right? So you are asked to find out a radius of curvature. Alright, so this is the given part. So what you are going to find is 1 by f is equal to n 2:1 minus 1 by r1 minus, this is lens maker formula. This is lens maker formula. Now look at here, the problem says that it is the Plato convex lens provided R1 is some finite value which we are going to find, and R2 is going to be infinity. This is a plane. We discussed last time that plane surface has infinity curvature. Alright, so this is what we have. So therefore, I say this is equal to how much? 1.5 minus 1, 1 by R1, 1 by infinity. 1 by infinity is 0, right? So therefore, 1 by, what is that? 0.3 equal to 0.5 divided by 1 by R1. So R1 is equal to 0.5 multiplied by 0.3. Alright, so what is this? This is equal to 0.15 meter. So the curvature of this plano-convex lens is 0.15 meter. I write here radius is equal to this, right? This is going to be 0.15 meter. This is the radius. Alright, now next problem. A convex lens made up of a refractive index N1 and is keeping a medium of refractive index N2. A parallel ray of light are incident on the lens. Complete the path of ray. Alright, I have three conditions. I will go one by one. Condition number 1 is that N1 is more than N2. N1 is more than N2. So I have a convex lens like this. Alright. This is N1. This is N2. This is N2. So N2 is less than N1. So I have a parallel beam of light approaching it. So now you are asked to complete a ray diagram, right? So therefore, this is principal axis. So this is converging, right? Why? Because ray bend towards normals, away from normals, then towards normals, away from normals. So this is the first ray, and this is going to be a focal length. This is the first ray diagram. Now the second, this is the first problems. Second problem is that if N1 is equal to N2, that means of a same medium doesn't change. That means this is the first one. The second says that N1 is, that means ray doesn't undergo any refraction when a ray passes through a same medium, right? So this goes like this. So this is N1, this is N2, this is N2. So ray doesn't undergo any changes. Why? N1 is equal to N2. No refraction takes place in a same medium. So this is the second case. And a third case tells you that what about if N1 is less than N2? N1 is less than N2, then you have just the opposite of first case. A first case is converging, then the third case is going to be diverging. Look at here. This is N2, N1, I'm sorry, N2, N2. So N1 is less than N2. So look at here, this goes like this, then away from normals, then towards normals, alright, then away from normals, then towards normals. So this is what? This is diverging. And this is converging, and this is diverging image. Okay, so this is the case. Now, next problem I have this. The problem says that a converging lens of focal length 6.25 centimeter is used as a magnifying glass if a near point of observer is 25 centimeters, that is G is equal to 25 centimeters from eye, and the lens is held close to the eye. Calculate the distance from the lens. You are asked to find distance from the. So that means, look at here. You are asked to find out U. You are asked to find out U. And what is the focal length? 6.25. And what is V? V is minus 25 centimeter. G, which is G is minus 25 centimeter. All right. So how to find out? Again, I'll use the thin lens formula, 1 by V minus 1 by U. You are asked to find U. All right. So therefore, 1 by U is equal to 1 by V minus 1 by F. Okay. Now, I will use here 1 by U. What is V? 1 by minus 25 minus what is F? F is equal to 1 by 6.25. Okay, everything is in centimeter. And then look at here, minus 6.25 minus 25, and then 25 into by 6.25, and 1 by U is equal to, you just add out, and finally we get, I will just do the, finally we get U is equal to minus 1 by 5, and U is equal to minus 5 centimeters. So you do this calculation, alright, I will take note, I won't take much time. So you do this, you will get finally 5, so therefore U is equal to minus 5. So minus means in front of lens, and then again it's true, right? What is the focal length? Focal length is 6.25. Unless you put within the focal length, image won't be virtual. So therefore, yes, it is true that U is equal to minus 5 centimeter. All right. So that this position lies within focal length. Therefore, image is magnified, virtual. What we normally find in case of magnifying glass. This is the first problem, and second problem is what is the linear magnifications? What is the linear magnifications? What is the linear magnifications? So linear magnifications is equal to 1 plus G by F. 1 plus G by F. And how much is that? 1. G is 25. F is how much? 6.25. And roughly we'll get 5. So magnification is 5. This is a linear magnification. That means when you keep image at near point. And this is a linear magnifications. Now second one is, what about angular magnifications? This is angular magnifications. When you get angular magnifications, when you keep image at far point. So therefore, this is going to be 25 divided by 6.25, you get 4. So linear magnification is 5 and angular magnification is 4. Yes, we know this is 1 less. However, we prefer this. Why? Because this doesn't give strain. Alright? You can view object for longer period of time. Yes, now next problem I have is a beam of light converges at P. It is something like this. I get a beam of light, something like this. This is P. A beam of light converges at point P. Now a lens is placed in a path. Alright? Convergence beam, part of the convergent beam, 12 centimeter from P. That means I am going to keep lens something like this. Distance is 12 centimeters. And now, at what point does the beam converges? If a lens is convex, focal length 20 centimeters. So this is the given. Given is that focal length is how much? F is equal to plus 20 centimeter. And how much is V? How much is U? U is equal to 12 centimeter. So this is one object. P act as an object. P act as an object. Act as an object for lens. P act as an object for lens. So therefore, I am going to keep this as U. Therefore, U is equal to 12 centimeter. And then you are going to find out focal length. What is the point of this? That we are going to find out final image. So therefore, 1 by F is equal to 1 by V minus 1 by U. Alright. What is V? To find out what is U? U is 12 centimeter. Goes up. V is equal to 1 by F plus 1 by 12. And then which is equal to F is how much? F focal length is 20. What is that? It is 12. You find out LCM, alright? Finally, answer would be 75 centimeter, right? Do this. 8 divided by 60. When you do this, there, and V is equal to 60 divided by 8. This is the answer. It is roughly 7.5 centimeter, right? 60 divided by centimeter. So this is the answer V. This is the V, right? So this has to be. Why? Because this is converging in nature. This will further, I'll do this. It is something like why? Because it converges. It further converges. This lens further converges a beam of light. Alright. So now the second problem is if I give instead of convex lens, if I give concave lens, then instead of converging it further, it diverges. So I just do like this. If I give here concave lens, it will diverges, it will diverges, it will diverges, it will diverges, it will diverges. Maybe finally somewhere here it is going to meet. Alright. So this is what we have. So again, what is the given? Given is equal to F is equal to how much? This is a 16, that is minus 16 centimeter, and U is again same 12 centimeter, and V is to find out. So 1 by F is equal to 1 by V minus 1 by U. Alright. And 1 by V is equal to 1 by F plus 1 by U. And what is F? F is minus 16. What is V? V is 12. And then 1 by V is equal to 12. 16th. What is the LCM? Alright. Let's say we do like this. 48. LCM is 48. We'll get 48. And then how much? 16 is 18. 3. Alright. And then what about this? 12 fours are. Alright. This is going to be 1 by 48. So therefore V is going to be 48 centimeters. So therefore, and that distance is going to be 48 centimeters. Alright. So this is all about, when I keep concave lens, it diverges and then bring an image beyond F. If I keep a convex lens, this will merge, converges and bring an image in front of P. Alright. This is all a problem. I could able to do this many problem, and you practice, you see this video and try to solve all the problems which we have done today, and try doing few more problems. Okay, thank you.